First of all, I want to say thanks to Stefan for inviting me here and this great crowd here. This is my first DAFx, and I've really enjoyed it so far. So, the word Shazam is sort of connotes a sort of a magical, wonderful, extraordinary thing that I guess is meant to surprise and delight. So let me take you back to the beginning, which was quite a while before the iPhone. Right, so here's the founding team. So there were basically 3 MBAs who were looking for a thing to do. So Chris and Philippe, so that's Chris Barton and Philippe, were looking for some technology to deploy in their project. They were MBA students at UC Berkeley, Haas School of Business, and of course what you do is back in the year 2000 timeframe, drop out of school and start a business, but they'd actually finished and were looking for some technology, and they went around asking various professors and trying to find a technology. Anyway, so what the technology needs to do is overcome all these different distortions, bad speakers, noise, voice compression, noise cancellation, reverberation, and all the challenges that you would imagine you would have to overcome in order to have a service like Shazam using a mobile handset to recognize music. So at the time there was no scalable technology, so we had to invent it. It seemed like a kind of a daunting task. So Chris and Philippe and Dheeraj went around looking for whether there could be technology. They did a lot of due diligence in the literature, and the answer kept coming up no. There's no such scalable algorithm. But then one day they encountered this man who said, it should be doable. There's an existence proof in that the human ear can recognize music in a noisy environment. So it must be possible. So Chris said, okay, well, we'll put on a project plan. Let's see. They would develop the technology basically there. See, they're sort of behind schedule because it was already, I mean, it wasn't until much later that we actually launched the service. But let's see, yeah, so they would scale the system up, and within basically a year, they would have a service in Europe and Japan, all working around the world. So that was the project plan. And then they found me. I was, they introduced them, or Julius introduced them to me, and I guess I really didn't know what I was doing. I was just winding down my previous company, and which was merging with Universal Audio at the time. So go to the state-of-the-art technology back in year 2000. This was the Nokia 3310. It had a 84 by 48 monochrome screen, and it could make a phone call and receive a text message. So that was like 7 years before app ecologies became viable. So we went around collecting data. We were tapping off a phone line, and okay, so then I was thinking, oh, it really is impossible. Like all those consultants that the guys talked to they were right after all. So I thought, okay, so how do I break the news gently to my co-founders and let them know that no, they shouldn't go out getting office space and hiring people and raising money because, well, it wasn't working. And then maybe I should look for other opportunities because I wasn't getting paid anyway. So I want to talk a little bit about the technology landscape at the time. So at the time, there weren't a whole lot of algorithms out there that could do what we needed to do. So some techniques were zero crossing, cross correlation, higher order cumulants, spectral flatness, various kinds of feature analysis, and transcription to MIDI and then string matching, and eventually Homo sapiens, humans. So we actually found a service in South Africa which was exactly this, where people would listen to music and tell you what it was. So briefly, looking at the various techniques, well, zero crossings, I don't know, I'm just being silly, but I can't really tell what's going on there. Cross correlation, so you get a strong spike in the middle if this is the same signal that you're trying to identify. But some distortions, like for example, as little as 0.1% stretch in the audio basically renders the cross correlation useless. And 0.1%, that's enough if you have a sound source and you're walking to it, I think at about 1 foot per second would cause that much Doppler shift. Spectral flatness, I don't know, the left and right, the right signal has a lot of noise added to it. So its spectrum is dominated by the noise. And at the time, the performance of such algorithms, there were, so the database sizes were on the order of hundreds of tracks, and it would take seconds to process each recognition. And there's a little anecdote. The RIAA and IFPI, they had this beauty contest of music recognition algorithms at the time. And they had, for example, 2 conditions. One was lightly corrupted, which was plus 20 dB signal to noise ratio, and the heavily corrupted one, which was plus 10 dB SNR. So these seemed a couple of orders of magnitude less than what we needed. Okay, so I'm going to try to walk through a couple of innovations that kind of led me to developing the algorithm, and actually with Julius's help. So the first idea was to use spectrogram peaks. So the problem statement is to use this to find that. Okay, so spectrogram peaks are really great. I'm sure many of you have played with them. So it's sort of, one property is they sort of solve the energy partitioning problem between signal and noise. I mean, you can kind of see it where you have, like these are percussive events, and these are tonal events, and then stuff in between is maybe noise or some other kind of distortion. And I'm sure many of you have played around with this. So kind of a nice thing is the peaks tend to survive distortions. Hopefully a peak can pop up over noise and stay above even if you add distortions. If you do nonlinear, if you add nonlinear distortions, you get product terms, so you get perhaps peaks that are also multiples of the that peak in frequency. And of course, they're very important in audio compression or lossy compression. But a question is, how survivable are they? I mean, I'm sure everybody who was trying to do something like music recognition had played with spectrograms, and it's kind of hard to tell what's going on just by looking at it. So, all right, let's take a look at the reference spectrogram. Okay, so you see a bunch of grid patterns, which is characteristic of stuff like guitar and piano. And so the first thing you do is to look at the peaks. Okay, so here I've marked in blue peaks using, of course, just the local maximum. Sort of sorry about the coloring, dark colors there. Okay, so this is, with the spectrogram itself removed, let me go back and forth so you can kind of see, oops. So now we've reduced the amount of data by over 1,000, a factor of over 1,000. So you've gotten rid of all the kind of messy energy, and then you have this. So then the question is, how do you take this to index the, or to search in a large database? You have to create a huge database using these dots. And again, on the query side, where you have a snippet of audio, you want to use that to find similar patterns of dots. Okay, so let's look at what happens to the peaks when you add noise. Okay, so that's minus 3 dB SNR. Looks like that. And this is kind of a combined peak map where let's see, the blue points are from the original audio. The red points are from the noisy query snippet of audio. And the green ones are ones where the peaks survived. They're present in both the reference and the query. Okay, so let's take a look at the, so that's negative 3 dB SNR, negative 6, negative 9, negative 12 dB SNR. Okay, so kind of a surprising thing is that a significant number of peaks actually survived, and also without much distortion. They basically stayed where they were. And this is negative 12 dB SNR, and it sounds like. So despite that distortion, those peaks survived. Okay, so in summary, the extent to which the peaks survived was quite surprising. And this is actually key to the algorithm. And so one thing you can do is to create a score which is just the number of peaks that survived. And that's kind of a nice thing because the number of peaks, or the number of coinciding peaks that survived, the tail drops off as a function of the number. So the more points that match, the lower the probability of randomly matching a song in the database. And you get excellent precision recall as a result. But the question is, how do you get there? How do you go from that to a search, to be able to find such a location where the score is high? So one way of looking at this is to, okay, so imagine you have a strip chart with the horizontal axis being time, and if you take all the songs and you put them end to end, you'd for the number of soundtracks that we have, you might have a couple miles of horizontal axis, and the vertical axis would be the frequency. And so these are spectrogram peaks in the database, in the reference database. And so you can take your query points and just slide them along like this until, wow, look at that. They match up, and you could fairly confidently say this is a match. So that's the sort of brute force method. You can use this. The algorithm would work. and you'd be done. Except you've got something like, in our database, we have 45 million tracks. And so that's, if you look at the positions within each second, we have, for example, about 100 points. This ends up being about 1 trillion positions that you'd have to check. So even though the service would work, it might take a long time to search all those locations. So given that this essentially solved the problem, we needed to figure out a way to get there quickly. So then, thinking for a while, in terms of first principles, you have, I guess, trying to solve a problem from first principles, you are trying to, you look at what you have and where you want to go, and basically ignore everything else. So it occurred to me that you should try to increase the complexity of the features. So if you looked at that, in order to match a single point, there's not a whole lot of entropy. There's only, like, let's say, if you're using a 512 point FFT, there'd be 256 locations, and you'd only have 8 bits of entropy. So that really isn't very interesting for doing a massive search or search in a massive database. So I came up with this idea that I called combinatorial hashing. You sort of ask yourself, how can you get there quickly? By sliding this spectrogram along, you have essentially like an order n algorithm where n is like 1 trillion. So what's better than that is an order 1 algorithm, which is a bit faster than that. So you kind of rule out algorithms that require, for example, touching all the audio. And this is something that was done frequently. For example, if you're doing a cross-correlation and sliding this sample along and doing like a cross-correlation for every song, you're touching the entire database. And that would kind of slow you down. So that would be an order n kind of a search. So you think, OK, what is there? Well, I said to ignore everything that there was. But you look around and see what technology is there out there, what techniques are there to do something like what you want to do, and to have the same properties, like, for example, order 1 complexity. So a great example would be searching text documents, where you can find, let's say, 1 web page or even a few words out of billions of web pages and doing it in a couple of milliseconds. Text search uses hashing, where you're able to search in this large database using keys. So how can we do this? Well, the keys have to have a certain amount of entropy. For example, if you had 32 bits of entropy, you only need to look at 4 billionths of the amount of data that you have in your reference database. So that's pretty good. That means that you can, let's say if you had, for example, a gigabyte of data, and you had 32 bits of entropy, then you'd end up with like a 1/4 byte of information that you'd pull back on average. And just for perspective. So if you're looking at 45 million tracks, if you're doing this kind of a hash search, you would pull back a very small proportion of your database for every query you did. OK, so a problem with this, problem is the noise. So let's say you have a reference piece of audio, and you go to a distorted query. You have spectrogram points that go missing due to room acoustics, or perhaps noise might cover some of the peaks. And then, so you have noise, which also injects extra peaks into your signal. So you win some and you lose some. Kind of a key idea is what I call combinatorial hashing. So like I said, each individual peak, if you're searching in a database, would have, you'd find a lot of information you're pulling back. So you want to increase the entropy of your keys, and you've got these patterns of dots, and you hope that combinations of them are fairly unique. So one example would be to compute hashes out of tuples of points, for example, 2 or 3 or 4. And let's say, for example, let's take a pair of peaks. You can, out of a snippet of, say, n points in your query, if you did a complete combination, you'd end up with, let's say, k times k minus 1 over 2, which would be kind of a square. The amount of data you would generate would be about the square of the size of the query. Well, let's look at the amount of information that a pair of peaks would have. So you see here, a given peak would have a time coordinate and a frequency coordinate. And so 2 of them, you could create a time invariant hash key by putting the values, f1 and f2, and the time difference into a token, and you kind of hope it ends up being somewhere close to 32 bits in order to speed up your search. So that's kind of promising. You go from about, let's say, 8 bits of entropy to, well, more than 8 bits. Let's say that'd be 16 bits, and then that time difference could be like another, let's say, 8 bits or so. So you end up with a 24-bit hash, which is getting somewhere close to 32 bits, and it's a lot more than 8. Okay, so a problem with that all-to-all connectivity is the number of points ends up being sort of proportional to the square. I mean, the number of keys ends up being proportional to the number of points squared. So we want to avoid this sort of a combinatorial explosion, this kind of quadratic explosion. And so a way to do that, and the way to limit the number of keys, is to, well, limit the fan out. And so the way you would do this, you would go across the spectrogram, find sets of what I call anchor points, and for each point, link to a target zone. And I'll show you what this means. Okay, so here are, let's say, a bunch of points, and you pick a point. Let's say that red point would be an anchor point, and each one connects to a number of points in what I call a target zone. And then for each pair of peaks, each edge, you can create a hash like I showed earlier, like the T1 F1 and T2 F2. And I didn't quite limit the number of points, but let's say, I don't know, you say, like, pick the top 10 points. And so you do this for anchor points, various anchor points throughout your query and your database. Okay, and each one of those edges ends up being a key in your database search. All right, so let's take a look at what happens to a degraded signal. So this is, again, -3 dB SNR. And you do this kind of a peak analysis, and you connect anchor points to target points, and you just kind of do this thing. It's not an all-to-all graph, so and you can kind of see each edge has a bit of locality due to the target zone selection. All right, well, so now, so earlier I got rid of the spectrogram, and then now I'll do the same, and look at that. So going back and forth. So again, we've reduced the amount of information, let's say, by, let's see, about a factor of 100. Going to the peaks was about a factor of 1,000. And doing a combinatorial hash, you end up with more tokens, but it's still kind of manageable. So like 10 times 1,000th is like 100th. So let me show you what happens next. And this is a really important slide. It shows you why we have such high immunity to noise. So in these sets of points, let's see, like those points, for example, you don't know what is signal and what's noise. Okay, so you've got a mix of points that are what I call good, they belong to your signal, and points that are from noise. And there are four kinds of linkages. So you have good to good, good to bad, bad to good, and bad to bad. So the ones you're interested in, the edges or keys you're interested in, are the good to good. And these are all essentially garbage. Then you take a look at what survived, what good to good edges survived. So that's looking kind of promising. And then let's take a look at what happens. All right, so this is, I think, negative 12 dB SNR. Quite a few edges actually did survive. Surprisingly many points survived, and surprisingly many edges survived. So sort of in summary, we've taken an order n possible algorithm that would work and converted it into about order 1. Well, you first index the database, and that's kind of slow. That's basically order n, but that's offline. And then when you're doing a query, you have a limited number of points and edges that you're searching with, and it's basically order 1, assuming each hash search is order 1, which if you studied computer science and Knuth, you'd see that. And the links, the edges have good entropic properties, much better than a single point. And then you control the combinatorial explosion by just limiting the fan out. Okay, so now this is looking kind of promising. And only a few links need to survive in order to suggest a good recall and precision in your search algorithm. Okay, so key idea, and when I'm generating all these garbage linkages, only a few need to survive. You've got a large number of effectively unreliable fingerprints. And to give an idea, in a case where you have, let's say, negative 10 dB SNR, let's see, about 90% of your points are due to noise, and 10% due to signal. And let's say the probability of each is, or the target points versus anchor points is about the same. So in that case, if 10% of your points survive, the number of edges that survive would be about 1/100th of the edges that could be created from a query. So it could be like 99% of your hashes could be garbage, and you'd be able to theoretically find very good candidate locations within your database. But then even with this enhanced entropy, using the idea of combinatorial hashing, it's kind of not really enough. So I came up with this technique that I call, temporal correspondence. Okay, so the number of noise fingerprints could be like 100 times bigger. So there are some people who, in different fields, would look at a bag of features. So you have, let's say you had hashes that matched, and then you just simply count how many of them matched. But since you're pulling back all these tokens, and let's say the search brings back a bunch of values, these key value pairs, and 99% of them are garbage, looking at a bag of features kind of doesn't work very well because the signal is buried in so much noise. So what else can we do? Look at temporal correspondence. So this is, sorry, I have such tiny print. So if you have a pair of edges, so this is an edge that would be represented in a reference soundtrack, and this time it's a T sub r. R is the means reference, and the plus means it's a positive match, or it belongs to signal, and the other subscript is simply the number index. You see, okay, here's the distance between this point and the beginning of the file. And then this one, so this is the reference, and this is the query, and this distance here is, well, simply the distance from the beginning of the query file. And these are the same color, which means they're the same fingerprint or the same key or hash value. And then, again, here you have a pair of basically invisible dark blue dots that correspond to a match, and then here and here. So they have this relationship where if you take this time and subtract this time, you can see that the value should be here, and this distance here is the distance from the beginning of this file to the beginning of that file. So if you look at this, so this is the sum of this offset plus the offset to the beginning of the file, or of the query file. So this is true for all the correctly matching pairs. Let's say you had n matching such values, and they should all be essentially T0, except for slight perturbations in where the point actually ended up due to the distortion in going through the environment and with room acoustics and all that. Okay, so, but on the other hand, if you have incorrect matches where you're coming up against a point in your database, a position in your database that doesn't actually correspond to a match, but you have a number of matching hashes, you might find, okay, here's a match, and here's a match, and here's a match, and here's a match. And let's see, these two are about the same color. I can't tell which is which. So maybe those match and those match. So if you subtract, let's say, this time coordinate, or sorry, this time coordinate from that time coordinate, and create all the differences, each pair of matches creates some offset. And these don't accumulate. They're basically random numbers. So let's do a time versus time scatter plot. So what this means is, let's say you had time in the reference soundtrack, and then you have a query. So this is time in the query file. And where the fingerprints start to match, let's say there, so all the points here are correctly matching pairs of reference versus query fingerprints. And all these things out here are, let's say, matches, but they're not, they're coincidental matches that don't have anything to do with the actual match itself. Okay, so you take the time differences between the points, basically the time in the reference minus the time in the query, you end up with these values that should be the same, about T0, and all these are the thetas that are just random. So you plot those values in a histogram, the time difference histogram. So this time coordinate is now the time difference TR minus TQ. And you find that you get a very significant peak in your histogram. So the probability that a peak could be that high randomly is extremely small, like exceedingly small. And these are due to random noise. Those are all the thetas, and this is T0. So here, let's say, I don't know, 45 or so would be the point in the reference file at which the query corresponds to. The beginning of the query corresponds to, say, 45 seconds. And remember, only a few good points need to survive, or other links need to survive. And the really cool thing is, if you look at this histogram, all the points here, belong to your signal. This got a little silly here, but it's magic. So stuff just sorts itself out. You don't have to try to do some kind of a fancy source separation. It just kind of magically sorts itself out. So one question that people ask me fairly frequently is, well, what kind of a noise reduction algorithm do I use to pre-process my signals? I mean, after all, the stuff coming out of a mobile handset, especially back when it was a phone call, we were a dial-up service, you would think that you would try to condition the signal to be better for some kind of recognition task. But the answer is none. If you think about it, you can't apply noise reduction because you don't know a priori what is your signal and what's noise. So it turns out that noise reduction is harmful. And then you rely on the fact that stuff sorts itself out to figure out what's what. Okay, so in summary, temporal correspondence histogramming, or temporal difference histogramming, is a way to reject outliers, especially when your signal is mostly outliers. Another way of looking at this, okay, well, you can apply various line search algorithms like the Huff transform. You just want to find something that looks like, you have some kind of a temporal correspondence. Well, that's fine. And I guess I could have created a scatter plot with more noise. And there are many examples of where you can't even see this diagonal line. It's so buried in noise that you can't really see it. But you know that this should have a slope of 1 going between the query and the time axes. Because after all, the features, when they match, they should progress and march along at the same rate. All right, so we can find a signal in like 100 times or 100x noise, with 99% of the points being outliers. And so if you look at this histogram, to create the histogram, you have a number of matching edges, but the number of edges is fairly manageable. And so in order to create the histogram, you have to sort a list of numbers. And the sort is just totally trivial. It's order k, and k is on the order of, let's say, hundreds. And that's the total order is maybe a couple hundred times the amount of time it takes to do a sort. So you have k less than a trillion. So it's really fast, and well, no noise reduction required there. All right, so now we have an industrial strength audio content recognition algorithm, and it can do. We have 45 million soundtracks in our database, and it only takes a few milliseconds to do the search. And we can do fairly good recognitions, down to maybe -12 dB SNR. And it can handle all kinds of corruption, like additive noise, nonlinear distortions. All right, so the problem is solved, right? So we had this, when we started out, once we figured out how to do the recognition, we actually scaled up. At the time, we had a partnership with a music provider. We had about 300,000 tracks in our database, and we actually had IVRs set up as interactive voice response systems, like a voice menu system that would record the audio, take the query sample, match it against our database, and then return the result by text message. So we're up and running, and then one day one of the guys comes to me and says, "Oh, it doesn't work." I'm like, "What?" It's of course perfect. It should always work. And then so he said, he went to Starbucks and he got like 0% recognition rate. So then I had to go to the Starbucks and I asked about the sound system, got some coffee, and asked the manager. And so the manager said, "Okay, yeah, we have this tape deck." This is back in the year 2000, where they actually had mechanical playback systems. And so what they did was they pitched the audio, or these cassette tapes, faster or slower, I can't remember which. And then so the recordings were pitched up or down. And then the playback mechanism was pitched in the opposite direction, so they would sort of cancel out and you get about the same, the original speed. And I thought, this is crazy, why do you do that? Is it to put more music on each cassette? And he said, well, it's to prevent employee theft. So if you imagine these cool soundtracks, and you had 1 million Starbucks all around the world in Galaxy, then that's actually a lot of tapes. And if each one cost like $5, let's say, then that's a lot of money. So they're saving and preventing theft. But the thing is, it wasn't perfect. So if you look at this proposed, or this example Fingerprint, F1, F2, T1 minus T2. All right, that gives you a fair amount of entropy, and it gives you really good fast search. But if you're in Starbucks, it didn't work. Because all you need to do is, and a key point here also is that it's a exact hash. We look for exact hashes. So there may be hashes where the points basically survive, but the frequencies are off by, let's say, 1 bit. And then the hash doesn't work anymore. And then, especially in Starbucks. There are these guys, you may know this group at Johannes Kepler University in Linz in the computational perception group, and they're really a bunch of great guys. So recently they submitted they announced their PhD theses. And so I was reading one by let's see, what's his name? Zonleitner. It's really well written. I recommend reading it. And so he caught on to this point, and usually somebody in the crowd will ask me how do I handle speed differences? So references my 2003 paper that I presented at the ISMIR conference. And so basically, he points out that the hashing model, however, does not exhibit robustness to any type of scale modifications, which is totally true. He's totally right. And here's an interesting plot. So what I call time skew is timescale modifications, and this is frequency scale modifications. So along this diagonal line, or this direction, these are ones that are, each dot would be a recognition. And in the recognition process, we look at the time and frequency modification, like what percent did it get altered. So these are where the time and frequency were stretched, just a regular linear stretch, playing faster or slower. And these here have no pitch modification, but they're sped up by, let's see, in this plot, up to 10%. And then you see like little clusters. It's kind of hard to see in this plot because there aren't enough points. But there's a kind of a cluster like this. And if you notice, it's an integer percent value of frequency stretch. And you see another one here at 4%. And I hear that radio stations are often pitched up by about 4% in, well, this is simply played faster. Anyway, so this gives an idea of the kinds of distortions, speed, tempo, and pitch modification in the world that you would actually encounter. So speed is simply playing it faster or slower. Tempo is when you change the time modification, the temporal stretch, but with pitch corrections, so it sounds about the same, but it's simply faster. And then pitch is when you modify the frequency, increase the frequency without, or the pitch without changing the time scale. So like this point, for example, is where you play it faster and yet lower the pitch. And that as well, you're playing it slower, but you raise the pitch. So I'm kind of running out of time here. So an example would be to, if you want to create an invariant fingerprint, you find quantities that are immune to such timescale modifications. So for example, frequency ratios are immune and time ratios are immune, for example. And if you note that for timescale modification, that diagonal line or cluster of points in that time versus time scatter plot no longer has a slope of 1. And then you would use a line finding algorithm, perhaps the Huff transform or others, in order to find those points. Those points that have the linear kind of relationship. So in summary, I used spectrogram peaks, combinatorial hashing, temporal correspondence, and maybe should add creating invariant combinatorial hashes. So now we have solved the problem. We have this operational service with 45 million soundtracks, really fast search, noise immunity, and time scale, pitch scale immunity as well. And then, so this is a kind of a silly slide here. So that's arguably 10 to the 14th times faster than the prior art relative to year 2000 when we were looking at this problem. So you can just look at that. I mean, looking at the difference in the noise resilience, the size of the database. Remember there are like hundreds of tracks in the database, and so whenever we're bigger. I tried cross correlation. So this is, I'm kind of picking on cross correlation as a kind of a straw man, but to do 10 seconds against 100 tracks took like 370 seconds versus actually the time wasn't measured in microseconds, so we were like 3 million times faster. And I don't know, multiply all those numbers together and we're about better than 10 to the 14th compared to cross correlation. So I'm well over time, but let's look at some examples. So this is an actual sample from our dial-up service. And that's what it mapped to. And then beat Shazam. Okay, this is. That's the sample that I showed earlier at the beginning where I said it was impossible. And it made me almost want to give up. But. So notice the similarity. All right, here's the bonus round. So what does that match to? Turns out it matches to all of these. So the way this was created was to simply mix these soundtracks together and try to do a recognition on this. So that's struggle for pleasure. One of my co-founders was fond of the bolero. Okay, and then let's kind of go back. So this is an actual recognition. If you use the command line to submit the sample to the service, we would actually return all these results. In our app, we only return one result. Right, so, well, basically it works. Right. I don't know if we have time for questions. Right.
Thank you very much. We do have time for questions, so right. Questions, there must be questions. Not, does it work?
Right.
Yeah. Thanks for your talk. You're just talking about speed and kind of frequency shifting. Is there a limit to that, I assume?
Well, in the code, it's basically pound define.
Okay.
We just say how much we want to. It does slow things down. So we kind of decide, well, based on that scatter plot of the common modifications that we saw, we can use that to look at what's practical. Because we can't, I mean, we could do more, but the vast majority of recognitions are within, I don't know, 10% in speed, or even that's extreme. Yeah. Like I said, you get sort of breakage if you have a Doppler shift compared to the original fingerprint. So if you're walking like this fast, the recognition might not work using the original hashes. Yeah.
So thank you. Did you do experiments on how well the system performs on, let's say, different recordings of the same classical piece? Different.
Yeah. We have extensive experiments. I mean, there are certain genres where we don't do so well, namely EDM. EDM has fairly low entropy, and we do best when the entropy of the source material is fairly high.
How do you start with searching? Anywhere in database?
Well, yeah, we can. We're simply looking for locations within this database of like 10 billion seconds worth of audio, and we zoom right to it. There were algorithms at the time we started that would check only at the very beginning of each file, and that wouldn't work if you added a couple of I don't know, like 100 milliseconds of time delay. Then those wouldn't work anymore. But we basically, looking at the hash search, it's not particular to any location within this entire database. It just goes, bam, you've got a hash that corresponds to the matching location of the key versus key. Mm-hmm.
Yeah, thank you so much for the talk. I have two somewhat related questions. First of all, could you expand upon anything that has to do with thresholding out the good to good key points? And then second, might be related, might not, has to do with like, did you have to take any care when you used like the ratio-based approach to handle the scale and time modifications, and that it could allow you to technically latch onto another cluster of combinations of key points that are at a completely different time scale and frequency scale? Or?
Well, the ratio-based ones, for example, the triplets might have more entropy, in which case they're fast. You asked about well, essentially, you want to make the ratios robust. So one way to make it robust is to, for example, if you have 2 bits, then it's going to be really robust. But if you have 20 bits represented in the ratio, then it's going to be extremely fragile. So you do experiments and you figure out what's good. Thresholding. Well, it's a typical, I mean, you have, like, for any given noise condition, the sort of ROC curve, and you kind of pick what's good. So it's empirical.
Yeah, so is the, tell me what song is playing over the phone still the main application of the technology, or have you branched out?
Well, it's an audio search algorithm. If you notice, there's nothing specific about music. So, and we did some partnerships here and there. There's an example of, well, probably digressing into anecdotes, but where we're looking at television soundtracks, and then we noticed, like, there are different files that kind of matched, and they had nothing to do with each other. And just by looking at it or listening more carefully, we noticed there are certain sound effects. And so, for example, crowd noise would be embedded in both files, but they'd be completely different contexts, and we ended up matching the crowd noise. So to make a short story long, we do have other applications. We've been involved with rights management. It's well, public information, but we had a partnership with BMI, for example.
How did you test the quality of your algorithms? Was there some automated testing and ground truthing involved, or?
Not sure. Well, we got lots of empirical data, and we tweaked things.
Okay. And one more question, going back to the Starbucks century, with the first service, was it robust against tape speed variances?
Oh, you mean like, what do you call it? Wow.
Jittering of speed of the...
Actually can. Well, I speculate. We should be able to deal with time-varying stretch.
Thank you very much for the talk. I have two questions. How many fingerprints are actually extracted per second to recognize robustly?
That's kind of proprietary. Yeah, we are a company after all, and actually a lot of companies in our space apparently don't publish anything. There's all this, there's IP everywhere, but.
Okay, the second question, maybe the same direction. Could you please explain how much power is actually needed to match this huge content data?
Right. Well, at some point it does actually end up being kind of an order n algorithm, because there's only so much stuff that can fit on a single server. And then the overflow then becomes linearly proportional to the amount of stuff you have. So that's, but the search in itself is very, very fast. And well, it's public knowledge, but we use GPUs, because if it's fast, you can always make it faster.
Okay, well, thank you very much again for this wonderful keynote, Avery.
Thanks for having me.